Hello, this is Scott Dahman of PowerWorld Corporation. In this section, we'll take a look at PowerWorld Simulator's SecurityConstrained Optimal Power Flow tool. We'll also take a look at some additional features that can be used directly with the basic optimal power flow. We'll look at a couple other topics, including another way to incorporate the effective contingencies into the optimal power flow. And one way is to do that is to use flow gates or interfaces with contingent elements. And for a lot of users, that's actually a preferred method to using the Security Constrained Optimal Power Flow tool, just because it simplifies the modeling of contingencies, and flow gates often incorporate the constraints that are really important to solve in the dispatch. So what a lot of people don't realize is that what the SCOPF is doing, which we'll get to at the end of this section, is you take a case and you take a list of contingencies, and what you're asking the OPF to do is to find a dispatch, a least cost dispatch that's secure for the base case and secure for every one of the contingencies without changing the dispatch. Unless, of course, you have remedial action schemes as part of your contingency definition. And, in those cases, the dispatch might vary if the remedial actions are implemented. But other than that, if you just put in auto-insert a bunch of contingencies, it can be frustrating if you find that it's the case that there's not a single dispatch that's secure for all the contingencies. And so without having that detailed modeling, a lot of times you'll get results that aren't meaningful because you'll end up with a dispatch that's not realistic, because realistically there are remedial action schemes, and you can operate sometimes in some areas where a contingency might appear to cause a problem if you don't have that modeling. So flow gates often encompass just those contingencies and enforced elements that need to be solved in the dispatch as opposed to solved with a remedial action scheme. So we'll take a look at that, because for a lot of users, I think that's a preferred method of modeling contingencies. Certainly, if you want the detail of the Security Constrained Optimal Power Flow, it is available with that tool. We also mentioned a little bit when we looked at transactions between areas that you can have them dispatchable by the OPF. So we'll look at an example of doing that, and that's really kind of a hybrid option between having fixed transactions with multiple areas on one extreme, and the other extreme being having a super area control that looks like an ISO control with no restrictions between areas. You can also have a situation where areas are able to transact with varying megawatt levels, but only within a range that you specify, as opposed to an infinite range that you would get if you combine the areas into a super area. And then we'll also look at DC power flow modeling, because that's useful in the OPF for a lot of users because of the speed that it affords, and especially in the SCOPF, where you have even a longer solution process. You can simplify the problem quite a bit and speed it up quite a bit, and get rid of complications that can result in maybe instabilities because of inadequate reactive power support. You can simplify away a lot of those issues, but you do lose some abilities to directly model losses and to directly model reactive power flows. But the tool still allows you to approximate the effects of losses and reactive power flows, even if they're not explicitly modeled. So we'll take a look at that. So first of all, we'll look at interfaces with contingent elements, or flow gates. You can have interfaces that have these, and you also have to specify when you want these to be solved, because if you have a whole bunch of them, it can add processing time to the solution. So we give you the option to ignore these, or we give you the option to only use them in certain circumstances, like with the power flow and the OPF, but to ignore them during contingency analysis, for example. So let's look at an example with, we're going to use a 7-bus case, and we'll use the one called B7 SCOPF.pwb. in most of these examples. I'll go to File, Open Case, and then in the top level Training Cases directory, you'll find that one in there, B7SCOPF. Okay, so let's suppose, for example, we want to have an interface that measures the flow on a line during the loss of another line, and we want to have a limit associated with that. So in the 7-bus case, a simple example of that could be, let's say the line from 1 to 3 is taken out of service, and then we want to know then what the resulting flow is on the line from 1 to 2. We can do that through an interface. So we'll go to our Model Explorer, and then under Aggregations, we'll go to Interfaces. And the case already has some area-to-area tie line interfaces, but we want to add a specific interface. So to do that, we'll just right-click in here and choose Insert. And then we can call it, like a lot of flow gates have names like, you know, line 1 to 2 for loss of line 1 to 3 or something like that. So we'll give it that name. And then we can insert a couple elements in here. And for a simple example like this, we have one monitored element and one contingent element. So we can first insert our monitored element as a line and transformer, the line between bus 1 and bus 2. So that's just a simple line transformer element. We'll insert that. And then we'll insert a line open contingency element of 1 to 3. And then we'll click OK. So here's the interface and here's the elements. And then so the description of that second one is the contingency open line from bus 1 to bus 3. And then if we solve the power flow, we'll see initially it's not calculating anything for this. And the reason for that is because of this option that's described on the slide right here. The option to monitor and enforce contingent interface elements. The default is to not do them because, again, there's processing time involved. So you might want to ignore them. But if we're just creating 1 or 2, it's not an issue on processing time, and we do want to monitor them. So we'll have to go into the simulator options, which we can open from the Tools ribbon, and then go to the Power Flow Solution, first page, and then the next page, the General tab right here. And then we'll want to choose the second option, which means to compute these during the power flow and the optimal power flow, but not during the contingency analysis in SCOPF. The idea behind not doing them during contingency analysis is if we've got a list of contingencies, we might want to just process them one at a time without this interface also being applied. So, you know, we're in that case, we might be explicitly modeling the outages of different elements, including the ones that are part of our interface as well. So we wouldn't want to put them in there. And if we included them in the SCOPF, then it would be, you know, kind of like a double contingency that would be occurring all the time, because you'd have your interface that would always be monitored for every single contingency. So it would, you know, increase the dimensions of your contingency accordingly. So normally you would want to just say use the second option. So now if I choose that and now I do a solution, then it'll compute the impact from the outage. And it's just using linear sensitivities to do this. It's not actually taking the line out of service and then solving the power flow. It's simply applying the line outage distribution factors, which, for cases of interfaces where we've got megawatt limits associated with them, usually that's good enough. So it tells me that the base flow on the line from 1 to 2 is 89 megawatts. That's what's presently on there. If we look at the one-line diagram, we can kind of see that from these fields right here. And then we presently have 64 megawatts that's flowing on this line, which is the outage element from 1 to 3. And because 1 to 2 becomes radial with this out of service, then it's just going to end up carrying all of the flow from this generator. So it's pretty straightforward just to inspect and see that that calculation makes sense. If that's taken out of service, then we'll get that. And if we want to, we can associate some limits with it. And maybe those limits might be equal to the emergency rating on this line. So I don't know, let's look at the ratings that we have on this line. Are the A limit's 120, the B limit's actually lower than that, but let's just assume that an emergency limit, if the normal limit is 120, let's just assume that the emergency limit might be 130, and so maybe that's an appropriate limit to put on our interface. So we'll do that. We'll put in a limit here. I think this is going to adjust the A limit, but I usually like to explicitly change the A limit over here. So you can actually edit this kind of limit used field over here, but I prefer to know exactly what I'm changing, so I'll come over here and type in 130 for the A limit on that interface. And in so doing, we can see that it's exceeding the limit right now. But if we run the optimal power flow, then we can have it change the dispatch of that generator, assuming it's not going to hit a minimum limit. Let me just make sure that's not the case. Yeah, it has a minimum of 0, so we can back it down. Yeah, what I could do is I could run the optimal power flow now with that flow gate definition in there, and it will hopefully back down that unit in order to make sure that I'm not overloading that line. So yeah, in the optimal power flow, I'm not disabling any of these. I'll go ahead and solve the LPOPF. Click OK, and then what we can see is it did back down that generator there, so that now the flow on that interface is now at 100%, which makes sense because, again, this is a radial line. If the limit's 130, then you'd want a situation where if this line's taken out of service, you don't have more than 130 coming out of that generator. So again, flow gates are a good way, I think, for a lot of PowerWorld Simulator users to incorporate contingencies into the power flow, and you don't need the SCOPF tool to do that. You just need the OPF tool and a list of your flow gate definitions that you can model as interfaces, as we've done here. Okay, so this is what we just modeled right here, and the example on the slide has a 100 megawatt limit. We used 130, but same idea. So, and if we set the limit to 100 and we solve the OPF, then we would see it back down to 100. Because it was a constraint that was being violated with the initial OPF solution without that constraint, then we would certainly expect that introducing that constraint would cause the cost to go up, and it does, because we have to redispatch the generation around that constraint. Okay, so next we'll take a look at area transactions as OPF controls. And as I mentioned earlier, these can be kind of used as an option that's somewhere in between separate areas on OPF control or a super area. You can also use it in a situation where you have a neighboring area that's not on OPF control. Like maybe you don't have cost information or bids for all of the generators in a neighboring area, but you want to be able to model importing power from that area, from the entire area at a certain cost. So, like say for example, we have the option to buy power from our neighbor at $50 per megawatt hour. So we could put that bid in, and the area doesn't have to be on OPF control, and you don't have to have OPF enabled generators in that area you just simply treat the whole area as a resource and assign a cost curve to the export from that area. You can also have a condition where both areas are on OPF control, and again, this was the kind of the example I gave where you want the two areas to be able to transfer power, but only within a certain limit. So if you put the two areas in a super area, there's essentially no constraint on how much power can be imported or exported. It's just really the capabilities of the units themselves, and then also any transmission constraints that might be impacted by the transfer. But there's no limit on the transfer itself aside from that. But if you put the transaction on control, then you could, in fact, put a limit on the transaction. Yeah, let's just do an example. So we'll do one. In this case, here we have 3 different areas, and it looks like the base case is we have an export, again, from area left into area top of 50 megawatts, and that's fixed. So we looked earlier at the example of making a super area, in which case the transactions can freely float. But here, let's go to, under aggregations, we'll go to megawatt transactions here, and we can see we have the transfer between top and left, and it's 50 megawatts. We'll go ahead and open the dialog here, and we could make this a dispatchable transaction in the OPF by checking this box right here. Both areas are on OPF control, so there's no need to put in a cost curve for the transaction. If, however, one of your areas was off OPF control, or even if both areas were off OPF control, then you could put in, for the area or areas that are not on OPF control, you could put in a cost curve for using that area's resources, export resources. Anyway, we'll put in a minimum and a maximum for the transfer, and let's say we'll go between minus 100 and 100 megawatts. And then we'll just click OK. These export and import transmission charges are just some values you can put in that get added on to the total cost, but I don't think they really impact the dispatch itself. We can click OK on that. The other thing we want to make sure is that the transactions are enabled as an OPF control. So we would want to go into the OPF options and results and look right here and make sure that area to area megawatt transaction controls, the disable box is not checked, and here it's not. So that's okay. So we'll close that. And then, we might want to look at difference flows and compare kind of the before and after, again, like we've done in other examples. So go to Tools, Difference Flows, and setting the present case as the base case. And then go back to the add-ons and do the primal LP. And we can see how the dispatch changes. So here we can see, if we go to our area records, we can see that we're actually exporting 50 megawatts from top to left. So that's actually the opposite of what was done before. Well, I can see that too with the difference flows. So if I go to Tools and look at the difference case, I can see that the transfer went 100 megawatts in the direction of top to left. So it was going 50 megawatts left to top, and now it's going 50 megawatts the other way for a 100 megawatt change. And the resulting changes in dispatch are that this generator right here at bus 6 dropped by 100 megawatts, and this generator here at bus 4 increased by 100 megawatts, which saved a total of $341 per hour. So that's the new point. If the transaction is binding, then it would be up against a limit, and it would be in the basis as well, we would see. So, for example, let's go back to the present case and let's just tweak this. So we see the optimal power flow wants to dispatch this at 50 going from top to left. If we did something like change the minimum, well, we could leave the minimum the same. That won't change anything. If we change the maximum to say 25 megawatts, what's probably going to happen is that it will dispatch to 25 because it wants to dispatch 50. But then it'll become a binding constraint. So I can go back here to the OPF and then resolve. Now it's at 25, which is the maximum right here. And if I go into my OPF options results, okay, if I look at all the LP variables right here, I can see the transaction control is sitting at its maximum right here. If it were a marginal control, which is what we saw before, then we would see an entry here in the basis. But because it's sitting at a limit, it's not in the basis. You can go back here and change the limit back to 100. Yeah, now if I solve it, yeah, it's shown here in the list of basic variables. The area transaction is a basic variable, and it has a cost. Well, the cost is the underlying cost of the generators, but it's shown that it's in between its minimum and maximum. It's not sitting at a max anymore. So it's a marginal control. Yeah, and again, you can put in export cost curves if you're using this dispatchable transaction with an area that's not on OPF control. So, something that's on participation factor control, for example. You can put in a cost curve. Okay, yeah, and then we can look at changes. Yeah, with limits of plus or minus 100, we get a dispatch of the transaction of 50. Okay, one more thing we'll take a look at before we actually get into the security constrained optimal power flow tool is doing DC power flow. Again, this is a useful option because of the speed and because of the simplicity. You don't have to worry about bus voltages. You don't have to worry about reactive power flows and the nonlinear power flow solution. In the automation example that we look at tomorrow, we'll do a solution of several different time points, and we'll use DC power flow modeling for that because we're going to be, with each time point, we'll be changing the system load. That just works much better using DC because if you're cycling the load a lot, then voltage set points and switch shunt settings and tap changing transformer settings and phase shifter transformer settings, things like that, really need to vary as well with different load levels. And if you don't have all that data or you don't want to push all of that in, then the AC power flow is probably not going to solve as you scale load up and down like that. But you don't have those issues with the DC power flow, so it's very powerful. But we can't explicitly model losses, for example, when you're using the DC. So what we might want to do is store some loss sensitivities, especially if we want to do things like include marginal losses in the solution. So a good way to do that is to start with a full AC solved power flow like we have here, and before we switch it over to DC, store the loss sensitivities, and they can be stored from the present case, or if you have a table of loss sensitivities, you could use Excel to copy and paste those in to simulator and start with those. But of course we can also start from a solved power flow. So we'll go to the tools ribbon, sensitivities, loss sensitivities, and we can choose to calculate them for each electrical island, for example. And I'll click calculate, and then I'll switch this to be the user specified, leaving them at present values. And then it changes to an enterable field, which is shown here in blue. So I can change the number if I want, or I can leave it there. I can switch my power flow into the DC mode, and it can still use these numbers. It just can't compute new numbers because it can't compute them without actually having the losses being modeled. So I can hit close. Okay, so then I'll go into the simulator options and tell it to use the DC approximation. We'll go here and then go underneath the power flow solution options. We'll choose the DC options, and then we can check the box to say use the DC approximation. So once you do that, and then once you go to solve the power flow, you're probably not going to be able to get it back to an AC solution. On a 7-bus case, you can. On a larger case, you won't. So anytime you're using a DC approximation, if you want to keep your original case, you should make a copy of the file. Just save it to a new name. So we can check that. Then we have the option to ignore the resistance or ignore the conductance. So what the program needs to do, of course, is it needs to invert. It needs to use the admittance matrix in the equations. So it needs to invert the complex impedance to get the complex admittance. And at some point during that process, you need to assume that the real part of either the impedance or the admittance is equal to 0. And the first option is to assume that the real part of the impedance is 0. So that's the little r. So then what it's going to do to get the admittance is it's just going to invert the jx quantity. So you get 1 over jx for your admittance. Or you can choose to invert the impedance first and then discard the real part, and then that's ignoring the series conductance. So that's the second option. So you can do either one of those. The default is resistance. That's kind of simpler. The second one's probably a little bit more accurate because then you're still picking up the impact of the resistance on the imaginary part of the admittance, before you invert it. So you can optionally, for for tap changing transformers, they can have impedance correction tables because depending on the tap position of the transformer, the effective impedance that is actually seen looking into the transformer can vary depending on that tap position. So, by default, you ignore those, but you can include those as well if you have them. It's usually kind of a minor effect. And then same thing with phase shifting transformers. If it's at a different angle, then it might see different impedances as well. When you switch to the DC mode, you also lose the effective losses in the transmission network, but you can approximate those based on the current operating point if you want by building those into the load. So if you click the DC loss setup button, you can type in a multiplier for every bus if you want, or you can set them based on the present operating point before you solve DC power flow, either on an area level or a zone level. So this case has 3 different areas in one zone. If we set it based on area, it's going to look at the losses in the area and then apply the same factor to every bus in the area. So if I click set down here, it calculates the losses in each area, and then each bus has the multiplier that corresponds to the area that it belongs in. So it'll increase the load. You don't have to change the value of the load. If you say that there's 50 megawatts at this bus, it's not going to change that number, but internally it'll model it as 50 megawatts times this multiplier to compensate for the fact that the losses in the transmission network go away. So it's just moving those losses from the transmission lines into the loads. There's only one zone, so if we did that, that's essentially a case multiplier, and then every bus in the single zone has the same value. Or if you want, you can say, I want to use a loss value of say 2%. You can type in 1.02 down there, and then if you hit the tab key, then it'll say, do you want to change it for the whole case? And you can say yes, and then it'll just apply everything here. It's kind of the same as if you go to the buses and then just set all the values to a certain value. So I want to use the ones that are actually in the case, so I'll either do it by area or zone, and then click set. The other effect that gets lost is reactive power flows. So you can include those effects with the branch limits if you want, assuming constant voltages. So it uses a power circle method to estimate the reactive power flow that would go on the line, and then it just does the addition, the complex number addition of the megavars and the megawatts, that the megawatts that it actually calculates and the megavars that are estimated by assuming constant voltage, and then it can come up with a factor, a power factor with which it can derate the branch limits. And again, this is done internally. You don't go in and change your limits, and if you go into your limit monitoring settings or you go to your branch records and you look at the limits that are being used, those don't change. Simulator just internally can derate it, so you can do that if you want to. And then also with the loss sensitivities, if you did that first step that we did with telling it to use user-specified loss sensitivities, then you can incorporate those in the OPF when you switch to DC. So you can check that box and then click OK. And so then the first thing we notice is that the megavars go away, and then when we solve the power flow, we might see some adjustment as well, but shouldn't see too much, just because the losses go away and they get incorporated in the loads, which can cause some slight changes, of course, because instead of losses being distributed at the transmission lines, they're now distributed only at the loads. So yeah, now we can see down here that we've got a DC power flow, and then we can continue. We can carry on our business with the optimal power flow if we want. We can solve that, and we can still incorporate, because we're using user-specified loss sensitivity function. We can still, for example, calculate components of energy congestion and losses. Although, well, actually, it's not enabled in the area. I can enable that. The penalty factors or the loss factors are still in there. I just need to go in here to my area records in the Model Explorer. Say go to OPF areas, just like we did in the previous section, and choose to include marginal losses. So if we do that, yeah, so we can still come up with a resolution of the LMP into energy congestion and loss components, even though we're not actually modeling losses. We're just using static sensitivities. Yeah, this slide just explains again the option to ignore the little r or the little g, and again what that means as far as what gets ignored. The impedance is r plus jx. You can either have to assume that this is equals to 0, or you can take the series admittance, which is 1 over this complex number, which is this, and then assume that the little g, which is the r over r squared plus x squared, equals 0, and then this is the impedance that's used. So, and then a note about the correction tables and phase shift effects. And then the other options for putting the losses into the load, derating the branch limits, and using loss sensitivities for user-specified values for that. So again, here's the loss function for the loads, and then adjustment of branch limits. Okay, and then the checkbox there for using the user-specified loss sensitivities. Next, we'll look at the actual security-constrained OPF tool. With contingency analysis, we kind of discussed that ideally the system would be operated such that there's no violations in the base case or under each contingency. Actually, achieving that could be done through remedial action schemes, but in the absence of remedial action schemes, it would need to be done through a dispatch that doesn't cause any overloads. You can use the SCOPF to try to find such a dispatch and define one at least cost. So what it's going to do is it's going to seek again, a single dispatch. There's no redispatch that's automatically going to happen with the SCOPF. It's looking for a single dispatch that has no violations in the base case or in any contingency, with the caveat that a lot of times it's not going to actually find that, and there's going to be resulting unenforceable constraints. There's an additional outer loop that occurs with the SCOPF in addition to the optimal power flow bounces back and forth between a linear program and a nonlinear power flow solution. The SCOPF has that inside, and then there's an outer loop that gets wrapped around all of it where it solves all the contingencies. So, and most of the time, processing it is usually spent, it depends on the contingencies, how many of them are being considered, and whether it's a AC full power flow solution or what's set up there. The linear program is usually a lot faster than actually doing the contingency analysis, especially if there's a full power flow solution assigned to the contingency analysis. We talked already about the contingencies, and of course the SCOPF will consider any contingency that you've defined where the skip flag is set to no. So it'll process all of those and consider them. Just some examples of what could be included, and there's obviously many, many more things that you can do with contingency analysis besides just this. For purposes of this, let's auto insert. I'm just going to reopen the case as well. So go back to Power World Simulator and just reopen this, and we'll do an AC power flow, and we'll do it without the contingent interface in there too. And we'll go to our tools ribbon, and then we'll go to contingency analysis. And we can just auto insert the N-1 contingencies. And we'll just use the line outage ones. So then we'll click do insert contingency records. It'll add 11 of them. And on our options, we might, we'll just go ahead for this case and use a full power flow method and make up power using all the generators in the case. And we can see if we do a run of contingencies on this base case, we can see we have 3 of them that cause violations. So those are things that the SCOPF should dispatch around if possible. I'll hit close on that. And then from the add-ons ribbon, I'll choose the SCOPF, which will open a dialog here. And there's several options that pertain just to the SCOPF. It's going to use other settings, other OPF settings as well. So, for example, it's going to just operate on areas or super areas that are on OPF control. So a lot of the things that we looked at earlier in the Model Explorer for areas, again, you want areas to be on OPF control. Things like if we want to include marginal losses, we'd have to set those to yes. Things like generator AGC settings and fast start capability, things like that. That would all, all these kind of OPF fields apply here too. It's the same set of controls. The only difference is it's going to consider contingent violations in the basis matrix as well. So okay, so in our case here, we see if we just run it on the base case, before we've run the SCOPF, we can see we have some contingent violations. Yeah, like we said, it's going to initialize the linear program. It's going to run contingency analysis, and then with the basic OPF, it computes control sensitivities with respect to any overloaded elements. Here, it's going to compute those sensitivities with respect to contingency overloaded elements. Generally, if you fix the most severe contingency overload for any particular element, it would fix any overloads that occur on that element under less severe contingencies or under the base case. It kind of implicitly makes that assumption when doing the linear program iterations. Yeah, newest most severe contingent violation is what it's trying to take care of first. And then each of these loops, if you click the button that says run full security constrained OPF, it's going to do all of that for you. You don't need to know this other than just for your information. And then the process terminates after the linear program considers all the contingent violations. And yeah, like I mentioned, usually what happens is if it's able to resolve the most severe violation for any given element, it would usually help other violations as well. One thing that can happen, though, is that it can run the contingency analysis, store the sensitivities, fix all the worst problems, and in the process fix the less severe problems as well, and then come up with a new dispatch that causes new contingency overloads. It wasn't aware of those because the last time it ran contingency analysis was on a different case with a different dispatch. So it has to go back and run, or it doesn't have to, but you generally want it to go back and run contingency analysis again to make sure there aren't any new violations. And that's what it does in the outer loop. And then there's a setting for that right here. You can set the maximum number of outer loop iterations. There's usually not a reason to change these defaults, I've found, but you can if you want. So we go back here to, so we might want to put, I do like to do multiple outer loop iterations, and I'll usually set it to like 3 or 5 or something like that. And then when you run it, it'll tell you how many outer loop iterations it used. And ideally, you want it to use fewer than the number of your maximum, because then it stopped because it did all it could, rather than it stopped because it ran the contingency analysis the maximum number of times that you told it could run. And then here you can set the maximum number of contingency violations allowed per element. The default is 12. You probably really don't need that many, but I've never actually changed it from the default, I don't think. Because again, like we said in the slide before, if it fixes the most severe violation for any given element, it's probably going to fix the other ones as well. Yeah, and there's a button that you can pop open the contingency analysis form from there if you want. So there's some check boxes. One called Consider Binding Contingent Violations from the last SCOPF solution, and then also initialize the SCOPF with previously binding constraints. And this one's checked by default and this one's unchecked. And again, I just leave those kind of where they are. Checking the first one can prevent the SCOPF from hunting between having a constraint binding in one solution, then resolving it, and then going to another space where then it becomes an overload. The last time, you want to keep kind of in the basis any contingent violations that were considered from the last solution. Yeah, so normally you want to leave that checked, unless if you make a major change to your case and then the previous solution is more or less irrelevant, then you could uncheck it. But yeah, I normally just leave it checked. So, and then the other option is to initialize the SCOPF with previously binding constraints, and that forces the SCOPF to start with the same tableau from the previous solution. It can help speed things up if the system change is small. Yeah, I just usually leave that unchecked, but you could check it. If you wanted to manually step through each iteration of the outer loop, then you could check that option and then set the outer loop counter to 1 and then just repeatedly click run full security constrained OPF, and then you can see how it progresses from one to the other. And then by leaving the previously binding constraints in there, then the next time you run the outer loop, it'll remember those from last time. So anyway, if we run it, then we'll go ahead and run it by clicking the run full security constrained OPF button. And then it goes through. And then by the time it's done, it tells me that it processed 3 contingent violations and it ran a total of 2 outer loops. So that's good. It ran, I put a maximum of 3 in and it ran 2, which means either it cleared all of the contingency violations, or if there's any unenforceable, it still found the optimal point where the unenforceable overloads are still minimized. And then I can look at results. If I look under contingency violations here, it shows the 3 contingencies in here that it processed, and then the limits. So initially this value right here shows the amount that the flow on the lines in this case from the initial contingency analysis run, and then the limit on each one of these is 120. The new value is then what it sees after it runs the SCOPF. So 2 of them, one of them is a binding constraint where the new value is basically equal to the limit. It looks like there's some tolerance in there of 0.09, but it's approximately sitting at the limit. And it's got a marginal cost associated with it. So yeah, we can look at the bus marginal price details, kind of like we did before. Marginal controls. A lot of these are similar, or the same kind of display that we saw in the OPF options and controls. We can look at basic variables and then the costs associated with them. And then if we look at the basis matrix too, we can see shadow prices and sensitivities and things like that. The key difference being on the SCOPF, you have your constraints are specified as a combination of a constraint and a contingency. So the area constraints are all, power balance constraints are all listed as base case ones, but these other constraints for transmission lines have associated contingencies. And if it's a binding constraint, then it has a non-zero lambda or shadow price associated with it. And some of the other displays that we looked at before, like outside of this dialog, you can use here as well. Like if I go to my Model Explorer and I look at the OPF branches, it'll tell me if certain contingencies are, or certain elements are binding either in the base case or for a contingency. So this one is. It doesn't tell you in this what the shadow price is, because I think the shadow price in this table is always associated with the base case. So if you want to see the shadow price that's associated with the contingency, then you actually do have to look at the lambda here in this. So we can see that it's 525. So if you have a constraint that's unenforceable, then the value field associated with the slack variable would be negative, and you'd also have a lambda in here that represents the penalty cost, usually $1,000 per megawatt hour. And yeah, the LP basis matrix that we just looked at show element and contingency pairs. Okay, if we still had, I reopened the case and I didn't have this contingent interface in here, but that would then only be applied during the base case if you had this second option check, not during the contingency analysis. But it still could be a binding constraint if the associated contingent element is binding. And then we can look, if we compared the optimal power flow solution that we had before to the SCOPF solution, we might see that the case has changed. I did not update my difference flow base case, but I think it's still, it's still saved in memory from what I did before. So, if I compare the SCOPF solution to the previous OPF solution, I can see I do have a higher cost associated with those additional constraints, which makes sense. If you have interfaces with contingent elements, you can still use those with the SCOPF, but normally you would want to use the second option here. If you use the third option, then it would be applying those contingent interfaces simultaneously with each of your contingencies that it processes to.
If you need further assistance, please feel free to look us up on the web, give us a call, send email to our support line, or if you prefer to work with a particular Power World engineer, please feel free to contact that person directly.